And if you plot this in a correlated plot, where for each of the dots, for each of the samples, you come up with a dot of the valence band and the conduction band, you find a nice straight line. So that means that the concentration noise is correlated. That means here, if the conduction band goes up, the valence band goes down, right? That means if the conduction band goes up, the valence band goes down, the band gaps get larger or lower. Depending on what the concentration is, the band gap goes up and down, okay? It's correlated. That's nice. It's kind of intuitive. But within each concentration, it's uncorrelated. So the configuration matters. So the last example we can do is explore what happens if you make your system too small. If you don't have a system that consists of 3,000 atoms, but you now take a system that has only 140 atoms, your supercell that has only 140 atoms. That means you really sample different concentrations if you have this order, right? Because you have no samples in between, because it's a finite number of atoms, right? You can't achieve any old concentration, right? It's a discretized way. If you then do that, your histograms look rather spiky. And again, you can imagine that this is correlated, and indeed it is, right? Uncorrelated in the configuration, correlated in the concentration, and when the system is too large, you can almost see these little bubbles in blue being correlated along this line. Okay? The bottom line of that is, if you have small systems, the exact concentration, the exact number of atoms that you have in your nanosystems, in your alloy, is going to matter. And that your band edges will move accordingly. And it's a statistical process. That means you have to be cautious when you have systems that have a few atoms thick in one dimension. The details will matter. Even from this bulk calculation, from this numerical experiment, you can derive that, or get that insight. All right. So we can now put this on this chart and look at this configuration noise, and look at the actual placement of the aluminum atoms in the 3D domain. So we have noise around here, and let's plot this. So the configuration noise alone, so we have exactly 1,000 atoms, and we have exactly the right concentration. Then we get the valence band moves like this, and the conduction band moves like this. So it has an interesting spike at 40% of aluminum. That is where gamma and X are crossing. If I now allow the aluminum concentration to vary statistically as well, the valence band looks like this before, but the fluctuations are much larger as indicated. And the conduction band edge also fluctuates much more, but once it is becoming indirect, it fluctuates less. So at this crossover of roughly 0.4, the fluctuations die down. So also the interaction between the bands is what's important. And different bands are differently sensitive to fluctuations. So the points at X appear to be weaker dependent on the details of the concentrations than at gamma. Okay, so I'm ramping down this on a presentation on how large would you have to make a system for these fluctuations to go away. So now let's look at how large do you make that system to have the configuration noise to go away. So again, we set the concentration to exactly one value, and we trace and make this the expectation value of the valence band and the conduction band edge as a function of atoms in the system. So we make the individual supercell bigger and bigger and bigger and bigger and bigger. So we start from roughly 100 to where we did our analysis to 1,000, then to 10,000, and then 1,000,000. So here you see in solid line the expectation values, and in dashed lines the 1 sigma lines around it. And the interesting thing is, for the conduction band, it's even non-monotonic. It goes up and it goes down. Here's the sigma plotted as a function of number of atoms, so it gets much smaller, which obeys with the law of large numbers, which makes sense, right? You want this to go down with the law of large numbers. Now, if you do the same thing, but you allow for concentration noise, we now already know that the concentration noise is much larger, so the fluctuations are much larger, and it doesn't show this inhomogeneous, non-monotonic behavior. And here again, the noise, if you just plot the noise, you see it's 2 orders of magnitude larger, ballpark, or 1.5 magnitude larger than the configuration noise. So again, concentration noise dominates. Finally, there's something called clustering. And clustering can be explained roughly like this, where it's not clear that you have a homogeneous alloy, but you could assume that you have some local clusters of aluminum arsenide and then gallium arsenide, rather than a complete homogeneous system. And the simple, stupid way to do this in NEMO 3D is to say, I construct my geometry unit cell by unit cell. Okay, so I have a 8-atom unit cell and another 8-atom, so I stack my system together like Legos. If that's the case, I can throw the dice for inside a unit cell and say, okay, I'm going to throw the dice for every aluminum and gallium atom individually. You could be aluminum, you could be gallium. You could be aluminum and gallium. Or I can throw the dice once for the whole unit cell. So then I would have a whole unit cell of 8 atoms to be gallium arsenide. And then in the next cell, I might have an aluminum arsenide cell. And in the next cell, I'm just going to have a gallium arsenide cell again, depending on the choices. But that would give me sort of cubic chunks that are a little bit more clustered, rather than rolling the dice for every aluminum and gallium atom. If I do that, my band gap changes. My valence band moves up, and the conduction band moves also up a little bit, but the valence band moves up harder, sharper. And that basically means the gap gets slightly smaller. And the noise is getting a little bit larger, which makes sense because the local arrangements are much more noisy and you need to go to larger systems to have effectively the same system. And the fact that the gap goes down a little bit is kind of commensurate with what was seen in low temperature growth of algal structures, where you have clustering and the gaps do indeed go down.